So I got it. Bring this also here. Just hold on. Okay. Okay. And where is the... So I'm not able to see the zoom. Just 1 minute. Just 1 minute. Hold on. I'm just trying to bring everything into one desktop. Oh. Are you able to hear me? Is it still connected?
Yeah, we can hear
Hello?
you.
Because I cannot somehow... Oh, okay. Yes. Okay, so this is there. And I want to bring this into another window. Uh-huh. Just 1 minute. Yeah. Okay. I can do this now. Yeah. Okay. Right. So let us do a quick recap. Uh, so we had started with the hydrostatic equilibrium, which was dP by dr is equal to minus G m of r rho of r by r square. And then what we did was we took a specific case of a polytropic gas, which is pressure is proportional to rho to the power 1 plus 1 by n. Okay. And n is always a positive number. And then we also rescaled the radius by a length scale alpha, and xi hence was a dimensionless radial parameter. Then we defined another variable theta, which was equal to the density divided by the central density to the power 1 by n. So we had these three substitutions. And when I put all this in this one, I get n plus 1 into k, where my k is just the proportionality factor here. Okay, n plus 1 into k into the central density to the power 1 by n minus 1 divided by 4 pi g alpha squared 1 by xi square d by d xi xi square d theta by d xi is equal to minus theta power n. Okay, so this we had shown. And then we said, not yet chosen alpha except to say it has dimensions of length. Hence, now we choose alpha as n plus 1 k by 4 pi g square root rho to the power 1 minus n by 2n. And this makes the coefficient as unity. Okay, so I choose my alpha so as to do this because that convenience I have. And hence, I reduce this equation to just 1 by xi square d by d xi square d theta by d xi is equal to minus theta power n. So far, okay?
Yes.
Okay, so this is, so I had done this in detail, but this is just, I mean, brute force substitution and reducing it using this one. Okay. So let us, okay, and then what we said was, we considered different, okay, so then we need boundary condition. The boundary condition is as follows. So here, one thing you remember is that, okay, so boundary condition, we know is that P on the surface equal to 0. And I had told you why we need it. Because the outside pressure is 0. So on the surface, if the outside pressure is 0. So if the inside pressure just below the surface is non-zero, then there will be a pressure imbalance and the system will expand. In order to prevent this, we have, and since we want equilibrium, this should not be allowed, and hence the surface pressure is made 0. This is the reason for this boundary condition. And now we will convert this boundary condition into boundary condition in terms of theta and psi. Okay. So now suppose, okay. So if R equal to R is radius of the system, this implies that xi for surface, I call xi1 is equal to capital R by alpha by definition. Now, what should happen here? So this means at R equal to R, and hence at xi1 equal to R by alpha, pressure should be 0. Now, since pressure is equal to K times rho to the power 1 by 1 plus n, okay, then PC is equal to K, central pressure 1 plus 1 by n, which means that my K is PC by rho C 1 plus 1 by n. Okay. And now what I want is rho by rho C, I have defined as theta power n. And so rho is equal to rho C theta power n. And since P is equal to K rho power 1 plus 1 by n, P will be equal to K into rho C 1 plus 1 by n theta to the power n plus 1. Are you with me? Oh, hello.
Yeah.
Okay. So, and so you can actually substitute it. And since K is equal to PC by rho C power 1 by 1 plus n, it just means that P equal to PC theta to the power n plus 1. Okay. And hence, P equal to 0 implies theta equal to 0. And hence it implies for the surface xi1, which is equal to r by alpha, theta at xi1 should be equal to 0. So this is the boundary condition for this system. Are you with me?
Yes.
Okay. So this is the boundary condition. What is the other boundary condition? Okay. So this is, I will just arrange it here itself so that it is at one module. Okay. And the other thing which is required is that at xi equal to 0, r equal to 0, and rho equal to rho c implies theta equal to 1. Hence, theta equal to 1 for xi equal to 0. So these are the two conditions. At the boundary of the star, xi should be 0. At the center of the star, theta should be 0. And at the center of the star, theta should be 1. So with these boundary conditions, we solved those equations. Okay. And then we had solutions. Okay. You understand those things which I discussed last time, right? About how you get those solutions.
Yeah.
Okay. Anybody has a doubt? Things are fine. Okay, fine. So the solutions, I will just do a recap of the solutions. And the solutions are for n equal to 0, I have theta as a function of xi. So I will put it this way, just for keeping track of the n, I will say, okay, so for a given n. For n equal to 0, this is 1 minus xi square. So this is a function of xi square by 6. Then we had, when it is equal to 1, then we had sine xi by xi. And I did not do it for the case of n equal to 5. N equal to 5 case is very complicated to solve, although an exact solution exists. So I will not digress myself. Maybe I can just write it out and send it to you as notes if you are interested. But it's a very complicated series of substitutions, after which you get a fairly simple form, which is that 1 divided by 1 plus xi square by 3 square root. And these are the only 3 exact solutions which exist. Of course, it goes without saying that you can calculate these numerically for these. Okay. Now, let us just consider this schematically. So let's consider the case of the n equal to 1. Then what happens here? So I have, let me plot here. This is theta, 0, and xi. And at theta and xi equal to 1, this is 1. And at xi equal to square root of 6, theta is 0. That's where to get from here. And in between, it is quadratic. And so it sort of goes like a parabola like this. So this is the kind of profile you have for theta. And this implies that rho equal to rho c, because my n is 0. So it's okay. Now, remember that although rho is constant, theta is not constant. And that is because theta is being raised to the power 0 in this case. So even when theta varies, rho is a constant. However, since pressure is equal to Pc theta to the power n plus 1, you have pressure going as Pc theta. So the pressure starts with some central pressure here and drops down to 0 pressure, and that is what is defined as the radius of the star of the system. Is the logic clear? How you are fixing the radius of the system?
Yes.
Okay, fine. So now next we consider the case of n equal to 2, and there I just gave a formal solution last time, but there is something interesting which you need to note here. So in this case, you have, sorry, not n equal to 2, n equal to 1. Theta 1 and xi again. But now here it will be slightly different. Here, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this is equal to 1 as before. Which is the first, when does theta become 0 for the first time? What value of xi? Right? I mean, this is my solution. So what value of xi theta will become 0?
Pi.
Will at xi equal to pi, it will hit the first 0. But then at every integer value of pi, it will be hitting the 0. And so the solution for this will be something like this. It's like that Fraunhofer pattern, Airy pattern in optics. However, you see that this region is not, I mean, this region is not physically relevant. Relevant as rho is less than 0. So this point here is the first 0 of theta as well as rho. And so this is the point where and so the point is, if similarly, in this case, if you actually calculate P equal to Pc theta to the power n plus 1, which is equal to Pc theta square. So P will be 0 when theta is 0. And so this is the boundary of the star. So of the system. So the system is confined to, the system is confined between, okay, so xi has xi is equal to xi1, which is equal to pi, is the size of the system, and hence the total radius of the system will be equal to alpha times pi. Am I clear with this?
Yes.
Okay. And for n equal to 5, theta goes to 0 only for xi goes to infinity. So this system is of infinite size. These are all ideal cases.
Says, could you repeat what you told for the physically irrelevant?
Yeah. So the point
Because
is, look, see, in this region, theta is negative.
yeah,
Okay. And in this, for this case, rho is proportional to theta because n is 1.
yeah,
So you have density which is negative, and so this region is not physically admissible.
yeah. So
And
just
so what it means is so at this point, the system reaches zero of the pressure and then the system dominates. So this is just a formal solution, although it doesn't happen physically. So the validity of that solution is only in this region.
got it.
Okay. So it means that the system is actually of size alpha into pi. And on the surface, pressure is zero and the system is fine. It's in equilibrium.
Yeah, got it.
Okay. And now in this case, you have, it's of infinite size, but I will give a note. As we will shortly see, the mass is finite. It means that the system is spread to infinite size, but as you go far away, the density drops so fast that the total mass converges. Okay, we will just come to these calculations right now. Can I proceed?
Yes.
Okay. Now let us consider different cases. One is, of course, now calculating physical parameters. So the simplest physical parameter is the radius of the system, which we already know, radius of the system. So here what we will do is, we will say that xi1 is the first zero of theta versus xi for any n. So you can actually say xi1 n. So for the polytrop of index n, what is the value of xi where theta hits 0 for the first time? Okay. And then the radius r will be given by alpha times xi1. This is what I told you just now. Is this clear now?
Yeah.
Okay, fine. Now we go to the next interesting thing, which is the mass. Okay. Now, mass within a radius r or equivalent, or equivalently within xi equal to r by alpha. That's what I meant. That I call, either I call it M of R or loosely call it M of Xi. How do I calculate this? I have got M of R will be equal to integral 4 pi R square rho of R dr 0 to R. I have to be a bit careful. Okay, so let me be mathematically rigorous and call this as 4 pi R prime square rho of R prime dr prime. I mean, because the upper index is R. This is clear? I mean, this is what I'll calculate, right?
Yeah.
Okay, okay. And so this is basically equal to 4 pi integral R equal to 0 to R equal to alpha square xi prime square rho by rho c times rho c into alpha times d xi prime. Okay, I'm just substituting for in terms of him. And so this is equal to 4 pi alpha cube rho c integral 0 to xi prime square. Now, rho by rho c is basically theta to the power n d xi prime. All right. Is that okay? I mean, I'm just taking this alpha things out. ठीक है ना? Okay.
Yeah.
Okay. And so what is this equal to? Now I'll do one thing. I'll go to the Lane-Emden equation. In the Lane-Emden equation, I have 1 by xi square d by xi square d theta by dxi is equal to minus theta power n. And so d by dxi. So I just take xi square to the other side and integrate. I will have xi square d theta xi okay. Okay, so this 0 and xi will be equal to xi square theta n with a minus sign integral dxi 0 to xi. Are you with me? I've just taken it on the other side and integrated it. All right?
Yeah.
And so what is this? Just compare these two. Sorry. So let me just do one more thing. Let me shift the minus to the other side. Okay. Compare this and this. They are the same. Which means that I can write the mass within a radius r is equal to 4 pi alpha cube rho c xi square minus of d theta by d xi evaluated at xi. All right. Now, this you know because here, if we know the solution for theta versus xi, we also know d theta versus d xi. Now here there's an interesting thing it is that it shows, see, this side is positive. So this negative sign means d theta by d xi has to be negative, which is what shows that as we go towards the outer region, the density of the star decreases. In general, and n equal to 1, of course, it will be rather the pressure keeps decreasing. All right?
Yes.
Okay. I want to now calculate the total mass of the star. Total mass, I won't call it star, total mass of the system. Which is m is equal to m at capital R, which is equal to 4 pi alpha cube rho c xi1 square minus d theta by d xi evaluated at xi1. Where, as before, we have xi1 is equal to r by alpha. It's fine? Hello?
Yeah.
Okay. Okay. Yeah. So this is there. So this I have now got the mass of the star and the radius of mass of the system and radius of the system. And at this point, you will find something very interesting. Let me just call this as I had done before. Let me call this 1, comma n and 1, comma n. Okay, to indicate that it is for the nth one, nth polytron. Okay. Okay, so let me now go to mass versus radius of a polytropic sphere. And so here what I have is, so let me just summarize. So I have R is equal to alpha xi1 and I have M is equal to 4 pi alpha cube rho c xi1 n. Let me just call it minus theta prime xi1 n, where theta prime equal to d theta by d xi. Okay. Now what I can do, you see that in the expression for alpha, there is a rho c which is hiding. Okay. Let me now use these two. Okay, note that alpha contains rho c, and now eliminate, sorry, eliminate rho c to get mass versus R. So if we do that, then what we will get is the following. So if I just write it out, the alpha also, I will have R is equal to n plus 1 k by 4 pi g square root rho c to the power 1 minus n by 2n into xi1. And I have mass which is equal to 4 pi n plus 1 k by 4 pi g to the power 3 by 2 into is rho c. into rho c 1 minus n by 2, and there's a cube, times rho c. This extra rho c comes here as compared to the other one. And then I will have xi1 comma n minus xi prime at xi1 comma n. And now I can actually eliminate the rho c from both these equations. And the interesting result,
Says,
which
won't there be a 2n factor, like
where?
rho c power 1 minus n by 2n, right?
2n, yeah, you're right. Okay. And so I can eliminate rho c, and what I will get is k will be equal to g m n minus 1 by n r to the power 3 minus n by n into a quantity I called nn, which if I substitute everything, then nn will be equal to n plus 1. I mean, you just have to calculate this and then get it. I mean, it's not worth doing it, because unless you do it, you will not be able to appreciate it. Which, of course, you can simplify even further by saying that nn is equal to n plus 1 by 4 pi 1 by n minus 1 xi1 n minus 3 by n plus 2 1 minus n by n into minus theta prime xi1 1 minus n by n. Is that all right? I just substituted it. And I hope this is, yeah, okay, fine. That is 1 minus, yeah. Yeah, so that is it. So basically it means that it depends on the slope of theta at the surface and the value of xi at the surface. I can calculate n for a given n, and I can find this relationship between mass and radius. One thing which I see is that for a given n, mn minus 1 by n or 3 minus n by n is equal to a constant. Okay, so let me just write it for convenience in two ways. I will write m is equal to r power, or n is proportional to r power n minus 3 by n multiplied by n minus 1, which hence mass is proportional to r power n minus 3 by n minus 1. Oh, I didn't see that you were just, okay. Yeah, I have just admitted you, yeah. Acha. So m is proportional to this. An alternative way, of course, I can write it is r is proportional to m to the power n minus 1 by n minus 3. Okay. Are you with me now until now?
Yes.
Okay. Now comes a very interesting aspect, which is a discussion on M versus R. And that is the following. See, if N is greater than 3, okay, then N minus 3 by N minus 1 is greater than 0, and more the mass, more the radius. Okay. If N is less than 1, then both numerator and denominator pick up a minus sign. So in this case also, more the mass, more the radius. But if 1 is less than N is less than 3, we have we have the exponent of R is negative, is less than 0. Hence, more the mass, less the radius. So you understand something weird happening here? It is like saying that if I pump more mass into the system becomes smaller. And can you envisage why this can happen? Anyone? Hello?
Contraction maybe?
Yeah, but why is it contracting?
It collapses due to
No pressure to
increased
balance.
gravitation.
No
No pressure to balance it.
Yeah, no pressure. I mean, no outward pressure to balance, and it collapses.
No, the pressure is there. That's why, because they are all equilibrium solutions.
No, I mean, the gravitational collapse is stronger than the pressure.
Yes. So what happens is, suppose you take a bucket of water and you add a bucket of water to another bucket of water. What happens is, of course, there is gravitational interaction between the atoms, but that gravitational attraction is so small that the decrease in size because of gravitational collapse is negligible compared to the increase in volume because of adding more amount. Whereas here, the system is gravitationally so strong that when you add the more amount, if there was no gravity, the volume will expand to twice. But the gravity increases so much that it actually crushes it further and makes it small. And in fact, such a thing happens in reality when you have neutron stars and white dwarfs. A heavier white dwarf or a heavier neutron star is smaller than the lighter one. The mass is so much that it contracts it further. Is it fine?
Yeah.
Yes.
Okay. So this is a very interesting counterintuitive thing. Which we have. Okay.
Sesh, can you explain the reasoning again?
So basically, okay. So the reason is, okay, if we add more matter, we expect it to occupy more space. But in such systems in which 1 is less than 1, less than 3, gravity is so strong that, okay, so, but in such systems, increase in mass increases gravity so much.
Is there a reason why it happens?
No, that's why, because of gravity.
Okay.
So for when you have such exponents, then the gravity is so for such polytrops, then the gravity is so much that the system, that what I would say, that the system has to become smaller to maintain equilibrium. Is the answer clear?
Yes.
Yes, Tesh, I have a question.
Yeah.
Wouldn't it be more, I would say, make it more clear to say it as density rather than mass? Because working with the
No,
density
density
makes it.
increases because it contracts. I'm asking why it contracts. That is because mass. No? Two particles attract
Yeah,
each
yeah.
other because of mass, and that contracts the density, contracts the size.
Okay.
And because the size contracts and the total mass is same, the density increases.
But you just said the mass is being added on, right? Then how is mass the same?
Oh, no,
If you
no, no.
add
Okay,
more.
okay, okay.
Oh,
Okay. So what I'm saying is, suppose you have two spheres, okay,
okay.
of same mass, same radius. The total volume is, so if the radius is r, then the volume of the first one is 4.3 pi r cube, second one is 4.3 pi r cube, total volume is 8 upon 3 pi r cube. Okay, so for this mass, for 2m mass, 8 upon 3 pi r cube is the volume. Now I put these two together. So previously, the attraction, gravity was only between the particles, among the particles in system 1. The gravity was only among the particles in system 2. The moment you put it together, there are the cross things. The particle 1 system is attracting particle 2 system also. Okay. And so the total mass, I mean, when I say total mass, I mean total mass of the two systems. So total mass remains 2m.
Okay.
When I put it together, because of this extra heavy attraction between them, it tends to collapse. Normally, what will happen is this contraction is negligible compared to the fact that there is an increase in volume because of increase in material. But when you have the n value between 1 and 3, the gravity is so strong that it offsets that and actually becomes smaller. Is it clear to everybody?
Yes.
Yeah.
And just could
Bharati?
you scroll the page up a little bit?
Pardon?
Could you scroll the page a little bit up? I just want to copy it. Yeah. Got it.
Okay, so I mean, so of course, I mean, one example is that these collapsed objects like neutron stars have this property. And I think in neutron stars, you can actually see that. What is the, yeah, Anirudh will be thrilled about it, right?
Very much, yes.
Yeah. So this property is there. In your BCC systems, you can actually see if that is happening.
I'm actually talking about it. I am running the code right now. What you're talking about, it's running in the back.
Acha. Okay.
So
Okay.
we do these very similar problem, but yeah, for BACs, it's we don't consider collapsing cases because it's very unfavorable in those numerically. To be honest, they are not considered stable. So
No. So
we try to
suppose you have
find.
two neutron stars which coalesce together.
Yes, Correct. That's
Or you can have
there, but
another thing. In fact, you
no.
can
The
have a
thing
better
is,
system. You can have a better thing.
but like
Suppose I
the thing
have,
is,
huh,
the thing is with self-gravitating BECs or BECs with gravitational potential.
yes.
Usually, what tends to happen is, as far as we see in literature, is that they tend to be extremely stable. Meaning, you can perturb it, you can change the shape how much ever
No,
you
no, no.
want.
Here also it is stable. It is
No, I'm
not
saying,
unstable. It becomes from one stable configuration to another stable configuration. The second stable configuration is smaller in size. That is what I am saying. It is not instability.
okay.
See,
No,
if
for us, it's
suppose,
considered instability.
yeah,
Any
it is not.
change in shape is considered instability.
So here I am
Yeah,
not
let's
considering
do different
instability. I'm
questions.
saying there is one
Okay.
stable, there is a one stable situation. When I put both these them together and wait for it to reach an equilibrium, the new equilibrium will be of a smaller size.
Okay.
That is what is being said. Because
That's not been observed in BECs, but okay, that's interesting. Maybe we have to try it out different
yeah,
parameters
I
or
mean, then you
something.
can
But
actually try it out because I mean, you will have to get the equation of state for BEC and actually try this out if it follows a
usually,
polytropic.
what will happen in BECs, I'll tell you. So,
Huh.
if you're considering two gravitational put belts, if you were to simulate numerically, you'll consider two gravitational belts, some potential, where the fluid will rest in. So, what usually happens with any kind of potential well is that not necessarily gravitational, is that when you merge two of them together, you will get a bigger well. You'll get a bigger well. So that's like taking, or in other ways you can look at it like taking a bigger well, creating a partition between them, and then reducing that divide and
No,
reducing
no,
that
I will
wall.
tell you where is the difference. See, the
Okay.
difference with gravity is just not the depth of the well. Gravity, unlike many other forces, is a long-range force.
Okay.
That is what makes a difference. That is why every particle attracts every particle which is even farther away. The problem is the following, I'll tell you. If suppose you take a particle and what is the number of particles in a given shell? What is the number of particles in distance r? It is 4 pi r square dr in a shell dr.
Yep.
So it means as you go farther away, the number of particles which are attracting it is increasing as r square and gravity is decreasing as r square. So it exactly cancels out. So the part, unlike say Debye shielding, where there's an exponential cutoff. See, the fact that gravitational force goes as 1 by r square and the volume of a shell as you become it bigger, it also goes as r square. These two cancel out. And so just because something is farther away, the gravitational effect
No,
doesn't die
Here
out.
is also, here the well is also defined in such a way that it falls off as 1 by r square.
Oh, I see. Okay.
Yeah. The well is defined exactly. We define it as like a harmonic well. So we just give it a harmonic shape, which falls off as 1 by r square. So,
Okay.
but like I said, maybe it might start off big. The merged neutron star, whatever, might be bigger. But I think at later configurations, it might contract, and we have to see where that happens. Like you
Yes.
said.
So, Anirudh, maybe we
But
can just
like
discuss it sometime. I mean, sit and discuss it.
sure, definitely. I'll finish the simulations. I'll send it to you. We have to sure.
Yeah. Okay, fine. So this is about mass and radius. Hey, I'm sorry for others. I mean, like we just got digressed into something. Okay. I mean, I think, but the moral of the story would be what others would have got it is that we are not doing this for purely academic curiosity, but there are some applications. Okay. Yeah. So fine.
Especially in my work.
Yes. Okay. So now let us consider using this. Now let us consider various physical parameters and let us consider the mean density. Mean density rho bar will be equal to total mass by 4 upon 3 pi r cube. And if we already derived the mass radius relation, that is m proportional to, what did we have? Or r proportional to, okay. We had r proportional to m power, what was it? n minus 3 by n minus 1. Correct? Yeah. So if I put this here and calculate my rho bar, I will get rho bar to be equal to rho c times minus 3 by xi1.
Sir, m power n minus 1 by n minus 3. Okay.
Is that so? Oh, yeah, sorry. Yeah. Okay, so rho bar equal to rho c times 3 by xi1. I mean, you just have to substitute it and see. Then you have xi prime calculated at xi1. Okay, I mean, multiplied by this. And again, since xi prime is negative, this is a positive quantity in this one. And hence you get rho bar in terms of rho c. Alternatively, you get rho c is equal to rho bar xi1 by 3, 1 by minus xi prime, theta prime at xi1. Okay. Now, what is the advantage? Now, rho bar I know. Rho bar is what? Rho bar is equal to the total mass by 4 pi on 3 pi r cube. And so from here, if I know for a given value of n, I can solve the Lane-Emden equation, find out where the theta hits the 0. I can find out what is the derivative of theta at that point and calculate xi1 and theta prime, substitute for this, and I get rho c is equal to xi1 by, I call it mod theta prime at xi1 times m by 4 pi r cube. So from mass and the radius of the thing, and if we know what is the polytropic index of the system, I can find out what is the central density of the system. Are you with me?
Yeah.
Okay. And once I do that, I can actually calculate the central pressure also, which is basically K rho c times n plus 1 by n from this one. And if I actually calculate all this, it will come out to be rho c is equal to now, okay, and now I substitute rho c in terms of rho bar, which is equal to 3m by 4 pi r cube, which I just did. And I will get rho c is equal to gm square by r4. It is that standard thing. Now, all what will happen is only numerical value, which will be different. The numerical value will be governed by, it is actually 4 pi n plus 1 xi prime, theta prime square at xi1. This is what comes out. I mean, this you're just to calculate it, when substitute and do it, just do it as an exercise, all these things. Is it okay?
Yes.
Okay, so this is the central pressure. And now we can come to, so this is the central pressure. And now let us come to central temperature. Now, if you want to calculate the central temperature, an essential input is the relationship between pressure, density, and T. And suppose I say I assume an ideal gas. Then P will be equal to rho into K into T divided by what? Something which we did, and that's where we use it here.
Mean molecular weight.
Exactly, the mean molecular weight. Okay. And so implies that the central pressure will be equal to the central density Boltzmann factor by mean molecular weight at the center, mass of the proton times temperature at the center. And I already know that PC is what? And so I will immediately, if I substitute all this, and also I will substitute for rho C here, and I will get that Tc, the central temperature, is equal to mean molecular weight times Gm by R times a quantity Yn, where Yn will be given by three. Okay, just a minute. So Yn will be equal to 3, I mean, just for, I mean, this you have to sort of calculate and see, just for completeness, I'm just writing it here. 3 by 4 pi, 1 by n. A quantity, just a minute. H, just 1 minute. There is a, just a minute. What is H? What is H? Just a minute. This is EV, which is a particular variable which I'm not able to figure out what it is. Mean molecular weight. I'm not okay. I'll just figure this one particular quantity. Just a minute. Okay, fine. Okay. So okay, that's fine. Fine. Yeah, I'll just tell you. Yeah. So it is y times yeah, this thing. Then the mass of hydrogen atom by Boltzmann constant multiplied by this very, I mean, you need to just solve this because it's a very messy algebra and nothing else. To the power 1 by n and multiplied by one more thing. I don't know where I should write this because that will, what is this? Is n of c, yeah. Multiplied by some quantity nn, where there is nn is nothing but this quantity here. So, I mean, all these physical parameters which I have calculated, please try to dirty your hands by actually calculating it. That is very important. Okay. And here there will be a very interesting moral. You will find that for many of the cases, the temperature is very high, which means much higher than the fusion temperature, which means these cannot be actually solutions to stars, many of these. Neutron star, yes. But most of the time, they may not be solution of star, but they are just solutions to self-gravitating spheres. And I will come to why is it that is important, which I already sort of indicated earlier. Because when a star gets perturbed, these are the intermediate regions through which the star goes. Okay, so let me just break for about 5 minutes and then I'll get back.
And says the mean molecular weight at the center, would it be different from from the rest of it?
It can. That's why I carefully put mu c.
Mu c, okay.
You see, because mean molecular weight depends on the state of ionization.
Yeah. And
so
that
can
depends
be
on the temperature.
Yeah. Yeah.
Okay.
Okay. I'll just come. Yeah.
Welcome back.
Okay. So let us now look at some properties of this Lane-Emden equation, why it is interesting. Okay. And so what I will call it, equation, rather T of the correct thing is of solution to Lane-Emden equation. And this is what is called homologous solutions. Basically, homologous solutions means there's a scaling relationship. And so let us just see this. Suppose I have two systems. Okay. And what I do is I have, suppose, for example, the central density rho c of one is, say, A times rho c of the other. And suppose the so suppose and the radius scales as xi1 is equal to b times xi2. Okay. Now, this implies that theta for 1 is equal to a power 1 by n theta for 2. Now, if I substitute both these into the Lane-Emden equation, then what I will find is, so suppose I substitute this, okay? So this will be, suppose I have 1 by xi1 square d by d xi1. This xi1 is different from the previous xi1. I mean, it is not the radius of this. It is any radial coordinate inside, Okay. So this xi1 square d theta 1 by d xi1 is equal to minus theta 1 to the power n. Okay. And now suppose I substitute this 1 in terms of 2.
Sir,
What will I have? I will have
hello.
1 by b square d by d xi 2 into b square. Am I right? Yeah. Xi 2 square. And then there is this theta 1. So d theta 1 will be a to the power 1 by n divided by b, not b square, sorry. You should have stopped me. This is just b. Okay. Is it correct? Just a minute. The b is cancelling out. Wait a minute. Oh. Sorry. Yeah. So let me just do it again. So this will be 1 by b square xi 2 square, which is from here. 1 by b d by d xi 2, b square xi 2 square, then a to the power 1 by n divided by b d theta 2 by d xi 2 is equal to minus, now you have theta 1, so that will be a times theta 2 to the power n. Are you with me? So I have just scaled one with respect to the other. No, are you getting it? So I have taken the system 1 and substituted the variables in terms of system 2. And so this will be equal to this, and this cancels out. And so I will have a power 1 by n plus 1 divided by b square 1 by xi 2 square d by d xi 2 xi 2 square d theta 2 by d xi 2 is equal to minus theta 2 to the power n. Now, this equation and this equation will be identical if b square is equal to a power, it says, small mistake, it should be minus here. It will be 1 by n minus 1. So what it says is the following. If I take this a system and go to a distance b time, so I'm at some point inside, and I go to another system where the distance from its center is b times, and it follows this law, then the density at the new point will be the same. I mean, okay, probably I should put it in a, okay, what I will do is I will actually solve out an example and show it next time. I understand it's confusing. Basically, it means the following, what I have been emphasizing, that if I know the solution to one system, just by scaling the radius and the density, I can get the complete solution of the other system of the same n. Okay, no, I understand this thing is not clear, but do you understand what is the aim?
Yeah.
Yeah.
Yes, sir.
Huh? So yeah, so that is the whole thing. That is, it happens because whatever be the central density, whatever, the final Lane-Emden equation depends only on the value of n. So all systems, independent of what is their central density or whatever, if two systems have the same n, in terms of the dimensionless variables, both will follow the same Lane-Emden equation. Okay, that is what I wanted to emphasize. Is that okay?
Yes.
So I will actually do this next time. Next time in detail, I'll do it. Okay. So okay, so this sort of concludes the thing about the Lane-Emden equation. I will give some problem and then I will, okay, so I will just tell one thing, a brief discussion on relevance of Lane-Emden equation. Okay. Now, suppose I have plotted mass on a log scale and radius on a log scale. Now, for stars, it is just a schematic diagram, not exact schematic. Stars, for example, suppose this is the way the line is. Remember that is a log-log graph, so the slope of the line is actually exponent of r. So if suppose you have m proportional to r power alpha, log m is equal to constant plus alpha times log of r. So it's a straight line. And suppose this is the normal star. And suppose there is a star with this mass and radius. And I have some value of n for which this is the Lane-Emden solution. And suppose the star is located over here. And there is some perturbation and some mass is thrown into the star. So what happens? The star immediately goes to a new position somewhere here. Okay. But now this is not an equilibrium position. So ultimately what the star will do is to go to a new equilibrium to this point. But this time scale, I call it dynamical time scale. Or I call it T2 or tau 2. At the same time, because of gravity, this can actually try to go to another value in that same polytropic gas with another mass and another R. What happens is, although ultimately it reaches here, suppose this time scale is T1, the T2 time scale is much larger than tau 1. So the star actually goes here, first goes here, okay, first goes here and then finally settles down over here. So for the intermediate time, when it has not reached that equilibrium in the main sequence star, the system behaves according to this Lane-Emden equation solution which I have given. I mean, do you get what I'm saying?
Yeah, but could you just repeat it in a short again?
Pardon?
I get it, but like, could you just repeat it again in a brief so that I
Oh, that
understand
is
better?
why. Okay, I fixed my sonnet. I'm not. Okay, can you tell me? Yes.
Yeah, I understand it, but could you just repeat it or reiterate it
Okay.
in a brief?
So basically, the tau 1 equal to time scale to reach a new MR value on the polytropic curve, MR curve, right? So it actually, from here, it will go to this one. The polytrop is the same. So for the same polytrop N, since the mass is different, go to a different radius. So if it is along the polytrop, it will just go here, ultimately. Is it okay? The step one?
Uh, yeah, but I'll just recall it again once again. I'm not sure if I get it completely.
Okay. So for a given N, I have radius proportional to mass to the power n minus 1 by n minus 3. Right?
Yeah.
If m increases and n is same, implies r changes depending on increase or decrease depending on the value of n, right?
Yeah.
Okay. So it goes ultimately from here to here, another value.
Yeah.
This is the mass, this is the radius, okay? But now the question is, what are the time scales involved? Okay. But now this is a star, and ultimately the fusion will readjust itself to bring it actually to another point over here for the new mass. So an M1 star and mass of star. So, okay, so this is the sequence it happens. 1 star of radius R1, mass M1. Okay. Okay. Some extra mass accretes. Okay. Onto it. Now, there are two things it can do. One is a new Lane-Emden solution or a new
Radius.
A new star, main sequence star. Okay. So for a main sequence star, mass radius goes like this. For Lane-Emden, mass radius goes like this. It is an intersection of these two. Now it has got perturbed. So it ultimately reaches here, because ultimately it is a fusion which will govern what is the equilibrium situation. So it will actually take it to a main sequence star. But it will take some time. So it will take a certain time scale. Okay. So this is a new Lane-Emden solution. Okay. No, let me just put it this way. So the extra mass accretes. Okay. Tau 2 is time scale, or I will call it tau ms is the time scale to reach a new point on the standard star M versus R line. Okay, that is, it should settle down over here. I mean, basically, suppose you're having a star, you throw some mass, it so equilibrates and it gives a new star of new mass and new radius. Okay?
Yeah.
Okay, so it will come here. But now, this is the MS. However, you have another time scale Lane-Emden, which is the time scale to reach a new MR value for the same N value. So that is, if suppose it does not, it should come here. This is the Lane-Emden equation. Now the question is, where does it go? What happens is, the TLE is much shorter than T main sequence. So what happens is, the star doesn't immediately settles down to a new normal star. It actually first drifts toward a Lane-Emden solution and gradually shifts towards this star, because the time scale taken for it to settle down from here to here is much more than here to here.
Yeah, got it.
Okay. And so in this large intermediate time scale, the system will be governed by a Lane-Emden equation and not the main sequence star. See, if you notice, I have always been saying a self-gravitating system when I'm talking about Lane-Emden equation and not a star. That is because not all Lane-Emden solutions can be stars. And the reason is, I calculated the central temperature here. Now, a star central temperature is fixed as the fusion temperature. So, the star will adjust itself not to keep it in a Lane-Emden solution, but it will adjust itself to keep the central temperature as 10 to the power 7 Kelvin. So now, as soon as you perturb the system, since it takes a long time for it to get to readjust to the new, readjust to a new configuration with central temperature to be 10 to the power 7 Kelvin, the in-between time before it reaches that, it actually is a much higher temperature in the center, and the solution is a Lane-Emden solution. Do you understand what's happening?
Yeah, but eventually it goes into the main sequence.
Eventually. So it is something like, okay, so something like, suppose I have, okay, so suppose I have something like, a potential like this. Ultimately, it will go in the minimum. But it can so happen that it is stuck for a long time before it goes to minimum. I mean, typically it is like tunneling, Okay. So, so ultimate equilibrium is this. But there is a metastable state. So this is a good way. So the Lane-Emden solution is a metastable state before the system goes into the ultimate equilibrium of a normal star.
When we say normal star, the equation of state will be different. That's what we mean, right?
The equation of state need not be polytropic.
Okay.
Okay. Now, and that's because the following: the moment you have a polytropic gas, your central temperature is fixed as we calculated. But for a normal star, the central temperature is not fixed from polytrop. It is fixed from how the fusion energetics are happening. So the central temperature is fixed at 10 to the power 7 Kelvin. So that is why, in general, a polytropic Lane-Emden solution may not be a solution to a star.
Okay.
Is that okay?
Yes.
And is there
So,
a expression for the time scales that you were talking about? Like, how do we,
okay. I think it will just be governed by collapse time scale and thermodynamic time scale. I'll find it out.
okay, will we be studying those things?
Yeah, I can introduce it. That's just a small thing to be introduced. Maybe actually the problem is in astrophysics, there are a lot of small things, like, and like you may do something, you may not do something else. Okay.
Yeah.
So I will tell you what is the next thing which I will do. So till here, they were completely theoretical stuff. So from next time, I will actually start with hardcore astrophysics, which involves, suppose I had talked about the hydrostatic equilibrium, and I just talked about thermal pressure. But if a star is very, very massive, then the central temperature then the temperature inside can be so large that the radiation density may be dominant over the thermal density. So these are called radiative stars. So I will actually now then talk about the structure of stars for which the radiation pressure is significant fraction of the total pressure. Okay. So I will do that. And after that, I will go over to the other interesting aspect called heat transfer within stars. I will first do the condition for convection to set up. And that convection is important even in the context of atmospheric science on the Earth. That same physics goes in. Okay. And then I will go to radiative transfer. So that is going to be the plan in the next few days, next few sessions. Is that okay?
Yeah.
Okay.
Okay. So I think
And
I'll stop.
please share this notebook file. Like, there were a lot of expressions. It was hard to note a lot.
Yeah, I will do that. I will do that. I will send you those expressions. Yeah. And not only I'll send you expressions, I will also give a problem set where you have to calculate each of them.
Yeah, that goes without saying. Yeah.
Okay. Okay then. Yeah.
Thank you, Sush.
Okay. Bye.
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 Thanks.
Bye.
Thank you, Sis. Bye.
Thank you,
Bye.
Sis.